Who's ready for electricity? All right, so let's begin. So just for everyone to keep in mind as we move forward, I know everything's open note, open quiz, but the uglies book is not going to be counted in that because it's not required as required text and not everyone's going to have it. All right. So as far as the quizzes and tests go, that's not going to count towards that. All right. So if you want notes out of it, take notes out of it, and that could be in your notes, but you can't use the book while taking quizzes. All right. So we can keep it fair to everybody. All righty then. Other than that, expect a quiz come this Wednesday. Same deal as we did last time. Basically log in. It's going to be underneath Blackboard. Exams. It's going to be called Quiz 2.
Professor, will Quiz 2 have all the questions on it, or would it be one question at a time?
It's going to have all the questions. So I'm going to change it up to do that. All right. So it's going to be all together. Basically 10 questions, one sheet real quick.
And is Quiz 2
When do you put the YouTube videos up? Like later today or like tomorrow?
Basically I do it about it all depends. Like last Thursday we had basically YouTube went down for like creators. So there was like a couple hours where I was trying to upload and it was just down and I couldn't upload. So basically I have to edit it so that way we remove some of the tail end, some of the beginning. So we go right into the lesson, then it has to render for an hour or so, and then it goes out. Usually within Tuesday morning, Thursday morning, or Monday night, Wednesday night. So somewhere around there. It's not going to be anything later than that.
All
right. Especially if we're going to have a quiz, I'm going to try and get it up relatively within that Monday or Wednesday night. All right.
Is Quiz 2 going to involve this and also the last lesson, electrical, and this?
No. So we're not going to quiz anything on that hydraulics 3.
Oh, okay. All right.
Yeah. So quizzes are just going to be only what was on last lesson. So so these slides right here are 36 or something like that, or 39. So if we only get to I'll post it saying we only got to slide 17. Then you're only going to be quizzed to 17, slides 1 through 17. And then the next day after that, it's going to be from 17 to, 26. Then you're only going to be tested on those. Okay. All right. Anybody have any more questions on that? Oh, and one thing I want to make perfectly clear, there is no extra credit. Okay. I've gotten emails about it. People have been asking me through the semester. There is no extra credit. All right. The fact that this is now open book is pretty much extra credit in its own. All right. So let us begin. And that's the other thing. Quizzes and tests from here on out, you should just have calculators on you. All right. Not a web browser calculator. Get used to using a scientific calculator, not a graphing, because that's all they allow for Coast Guard. All right. So get yourself a scientific calculator. And it should be defaulted that you should have one on you for all quizzes and all tests, and definitely for the final. All right. So let's go into electrical parameters. So a couple definitions to start off. We have charge, basically measured in coulombs, the amount of the element of electrical energy transport. Then we have current, that's in amps. That's the rate of flow of charge. So 1 amp is equal to 1 coulomb per second. Then we have voltage, or volts. It's the energy per charge gained or lost. 1 volt is equal to 1 joule over a coulomb. Then we have power, or i.e. watts. It's the rate of electrical energy production, transmitted or consumption. And then we have resistance, or ohms, which is the way it's measured, is the opposite to is the opposition to charge, flow measured as the rate of voltage or current. And then there's some quick equations there. And since we have 39 slides or something like that for this one, I'm going to post these right away after class. So these will be posted. You're going to get all the slides in basically one fell swoop. And then that way, if you want to follow along that, going through it, so you will have these for the quiz. So charge. Charge comes in packets of coulombs. It's either positive or negative. As magnets go, opposites attract, and like charges repel. One electron is equal to negative 1.602 times 10 to the negative 19th coulombs. So 1 negative coulomb is equal to 6.24 times 10 to the 18 electrons. You'll be surprised on how much this number actually comes up throughout your entire career as an engineer. So that's 6.25 million trillion electrons. That's a huge amount. All right. So here's where it gets interesting. So right here we have like a wire. It's an electric wire going off in 2 different directions. All right. And we have electron flow represented as the negative. All right. And then over here, we have conventional current. And this is where we actually talk about, when people talk about which way is the current going, it's going the opposite direction of what the electron flow is happening. All right. So when we take a reading, and we're actually going to be reading current itself, it's measured in amps. All right. And it's the number of coulombs, positive or negative, passing any point in 1 second. All right. So it's any point. That's why with an amp meter, you can't just connect an amp meter where if you had a light bulb, you can't just connect an amp meter off and take a reading that way. This isn't possible. What you need to do is you need to have the amp meter in between, or actually in line with whatever is reading. All right, it's going through a singular point in the line. So it's reading through the line. Another way to remember it as well is what, I don't know if you guys learned this trick, but as far as amp meters and between a voltmeter and an amp meter. So an amp meter, it's an A, it represents as an A, but it has a line going straight through it as a capital A. So it's just a straight remembrance of that. A voltmeter doesn't need to be in line because it doesn't have a line going through it. All right. An ammeter needs to be in line because it's splitting it with a line that's right there. All right. So that's how you can remember an ammeter needs to be in line with whatever it's reading. So you have voltage, energy in joules gained plus or lost minus by a column of charge moving from point A to point B. Voltage is measured between 2 points versus at a point like current. It's a comparison of potential. All right. So over here, we have a new symbol. All right. That's a symbol for a battery. It doesn't need to have all of these cells. Most likely what you will see is just something that looks like this. Or maybe it's not even that much. You might even just have a comparison like that. More often than not, it will look in that orientation. Having a battery symbol that is this large tends not to happen that much. So you have a 12-volt battery over here. So 1 volt is equal to 1 joule per column. Each column gains 12 joules through the battery. So this is where it's gaining its energy. Then we have a light bulb on this side, and each column gives up 12 joules through the bulb. So has anybody ever heard of that whole comparison of electricity to liquid flowing through a pipe? Of how it's been.
Sure, yeah.
So we're just going to do that comparison, just how as I talked about when we introduced refrigeration to you guys, and we were talking about a motor and how I said I didn't like that comparison because it didn't do it justice. This is an actual good comparison. It's a good way to think about how voltage works, how amps work, how horsepower compares to how what you know and what you're trying to learn at the same time is actually a very good comparison between the two. All right, so right now we're going to just do voltage. So voltage is similar to energy in pounds inch. It's gained or lost by a cubic inch of liquid moving from point A to point B in a piping system. So basically, if you have a 12 psi pump where 1 psi is 1 pound inch or inch cubed, so it's gaining energy through the pump just like you were gaining energy through a battery. And if you have a valve over here and you basically have it as a restriction, just like the bulb, each inch cubed gains 12 pounds inch through the pump, and each pound inch gives up 12 pounds inch through the valve. So you have voltage is about pressure. It doesn't equal each other, but it's a good comparison. Voltage is to pressure as current is to fluid flow. All right. So voltage is the pressure that's going through the piping. The current is the flow. It's your rate. All right. And then we talk about power. So same thing. We have a 12 psi pump over here, and we have a restriction and flow over here. The rate at which energy is delivered to a fluid is pressure times flow. So in English units, it's psi times gallons per minute over 1714. That is equal to horsepower. In SI, it's newtons per meter squared times meters cubed per second is equal to Newton meters per second, which is a joule per second, which is equal to watts. So rate at which energy is delivered to or retrieved from charge is voltage times current, which is about pressure times flow. So we have a battery that's doing 12 volts. So 12 times 1 watt supplied. We have each column gains 12 joules through the battery. Each column gives up 12 joules through the bulb, and 12 times 1 watts is consumed. All right. Notice what we have here as well. This is green. This is green. This is green. This is green. And this is green. So the big thing that we're noticing right here as we go through this is these PowerPoints are made up very nicely to give you guys a good indication when you're studying at home, what goes to what. All right. So keep that in mind when you're looking at these. So power. In most power systems, the source voltage is constant. Right? Just how people talk about if you have like a 12-volt battery in your car, or if you're using a AA battery, any of those voltage it's constant. So the number and type of loads turned on determine the current and power. So we have a 120 volt source. We have 60 watts is consumed at this location. Now, at the 60 watts, 0.5 of the amps is our current. All right. And as we go through 240 watts, 2 amps is our current going through there. And 180 watts is 1.5 amps. So we are basically adding up as we go through. All right. So 0.5 plus 1.5 plus 2 amps is 4. All right. And we're adding up our 60, 240, 180, and that's how we get our watts. So I'm going to leave that up for a second. So power and energy. The more items turn on, the more power we draw. The longer we let things run, the more energy we consume. Energy is equal to power times time, and watts times seconds equals the joules. So we are billed for energy consumption in dollars per kilowatt hour. A kilowatt hour is 1,000 watts times 3,600 seconds. So 3.6 million joules. So that's how, when you look at if you have any electric bills or anything like that, take a look at the power consumed. All right. It's all multiplied by this number. This is what your actual billing rate is. So before we go into resistance, any questions so far?
So how you're billed is $1 per kilowatt hour?
Yeah, so you would have an actual rate that they would calculate out, and that's all due to their numbers as far as how much it is to, actually produce that energy and everything like that. So that's how they
Okay.
actually, that's the number. So if you actually look at a bill, you will have this number there. And it's all basically how many kilowatt hours you used, and then it's multiplied by that, and that's how you end up. So you would have like how much money over kilowatt hours, and then you would have how many kilowatt hours you actually used. Multiplying those two, you lose these, but then you just have money you owe. All right.
Thank you.
Yep. And of course, hours get crossed out too. So any questions on what we went over through the entire couple slides that we went through? Remember, guys, stop me at any point if I'm either going too fast or anything like that. So let's go into resistance. What determines how much current a given customer will draw? It's resistance. So 120 volt, 60 watt bulb draws half an ampere because it has a resistance of 240 ohms. All right. So here's a basic calculation right here to get resistance. Those were those three formulas that were in the beginning. All right. So you have, oops. There we go. Right here, basically you have volts times watts or amps. Oops, sorry, that's power. Trying to do this from my head. So you have 120 volts times amps is equal to 60 watts. All right, because there's a resistance of 240.
Wait, I'm confused. What was the equation you were trying to write under the brackets?
Basically, I'm just trying to look at my notes and compare it to what you guys need. So you have three equations here. So you have I is equal to, do it shorthand, E over R. And then you have R is equal to E over I. And you have E is equal to I times R.
So basically the same equation, just put in different ways.
Exactly. So basically, I is equal to your amps. Your E is equal to your volts. And your R is equal to your resistance. Oh, that's current is I. Yep. So we have that. So, and then volts is equal to, and that's your actual flow, your potential energy there. Whoa. Didn't know I could do that. All right. So the higher the resistance to the movement of charges, the less current through the device. A bulb with 360 ohms, the filament inside of it, because remember, we're talking about old style bulbs, not LEDs, draws only 120 over 360. It's equal to 1/3 an amp, and consumes only 120 times 1/3. It's equal to 40 watts. All right. So the higher the resistance, the less current flows through the device. So we have basically a nice little diagram for you guys to remember. All right. This is everything as far as like what you're actually concerned about is like with Ohm's law. All right. Where, there we go. That's way better. So the way you actually work these is you cover up what you need, and then you're able to, if it's P time, so if you're looking for actual power, you cover up power, then you have voltage times current. All right. If you need current, you cover up the I, you have P over V. All right. So these are really nice ability to actually remember how to actually have all of these equations memorized. All right, you just have to remember the way these circles are oriented, and then you can find 3 or so equations from each one of these. All right, so you cover up what you want, and then you're left with what you need, what you actually have, whether it's power or voltage. Or if you're looking for resistance, if you cover up resistance, then it's voltage times your current.
Wouldn't it be divided? It's V over I.
Yes, it'd be voltage over current.
Yeah, you said times.
Did I? I'm sorry.
Okay.
So DC current, it simply means it's constant. All right, it's direct. DC current flows in only one direction. DC voltages remain at near constant levels. So DC voltage sources, you have batteries, you have DC generators or simply generators, rectifiers or electronic circuits which convert AC to DC. Rectifiers with additional voltage regulating circuitry are simply called regulated power supplies. So DC voltage sources are basically just like centrifugal pumps, nearly constant pressure with flow determined by a connected system. So this is an automotive, so basically like a car, DC circuit. So before we even start, right now, we have our ignition, we have our battery, we have basically our rectifier and voltage regulator, spark plugs, headlamps, radios, signals, turns, etc. And then we have our motor over here and our, God, what's the name of it?
Alternator.
Thank you. What do I do without you guys? So basically, as the alternator spins, that's going to be like our generator. All right. We have our engine, alternator, and as we go through, it's driving current through. All right. Some is charging the battery, and then some go to the actual systems. All right. So whenever you turn on certain systems, you're actually going to be having flow going through it. All right. So we're going to be constantly charging our battery. We're constantly sending flow through our radio, our signals, our turns, etc. Anything electrical in the system. So here's the big thing is when you see people, when they have alternators, all right, as I cross it out, what's the biggest takeaway from just looking at this drawing? How can you tell that if you have a bad alternator? What would happen if you're just driving down the road?
It like squeaks a lot.
Well, what if
the belt's loose?
So let's not even say the belt is loose. Let's just say it just completely fails. All right, it's
Things
unable.
start turning off.
What would happen?
Start the car, but it'll die out after 10, 15 minutes.
So
what is happening?
It's the car's relying on the battery.
This car is running only on the battery without receiving any charge back, right?
That happened to me once. It's terrifying.
yeah, my belt fell off my alternator.
My belt exploded.
Your bearings would freeze. So we're not talking what would happen to the alternator itself. We're just saying if we had all of a sudden we snap our fingers and the alternator disappears.
The car starts losing power.
I drove through Bridgeport.
So your car would start losing power. All right, very slowly it would be fine at first, but it wouldn't start next time. So that's what's going to happen here is that it's going to be, you would be able to run for a little bit. All right. But then as you're running, because we need spark plugs and we need a constant flow of electricity. So every single time we go around and we have a complete, I thought someone was getting changed in the chat. Every single time our engine goes through its power cycle, we have an actual spark plug that fires, and that's coming from coming from our alternator. All right. So that's why you see people that are driving down the road and you would see their headlights, they start to dim, the radio starts to die. Usually the radio goes out first. And that's how you would be able to tell that you have a bad alternator. All right. What would be a good alternator but a bad battery?
Car won't start.
The car won't
Battery
start.
doesn't charge.
Battery doesn't charge. But would you be able to tell just by driving?
Probably not.
You wouldn't be able to tell just by, if you were driving this vehicle and your battery was taken away mid-drive, you'd still be able to run.
Drive.
Say again?
Don't you need the battery to drive?
So if you remove the battery mid-drive while you were driving around,
It'll
you'd
stop.
still be able to drive because you have your alternator power.
All your lights would
The
be
only-
pulsating at different brightnesses because there's nothing to regulate that 12 volts that it needs.
So that would happen. You'd still be able to drive around. So if your battery is bad and you remove it, yes, you would have your problems there, but you would still be able to move forward. But if you removed your alternator from the equation, your car would die. You wouldn't be able to last very long because you would be running only on what's left in your battery. But if you remove your battery from it, you'd still be able to run. You may not run very nice, but you wouldn't die randomly, or it would seem randomly.
Would this happen with a diesel? Since diesels don't have spark plugs?
So what's happening with a diesel then?
It's just using the compression, right? So you'd still be able to run?
So
No, because you want to be able to have all the electronics running that run all the ignition and all the other stuff that happens on modern cars.
So if you had just a very basic diesel engine that was all heat and compression. Yeah, so you have your heat and compression. So on a basic diesel compression cycle that you have your crudely drawn piston, but there's no spark plug. So there's no electric charge. So all you actually have is your fuel going into your injector. It atomizes. So, you know, when you have a nice spray bottle and you're cleaning your house because of the coronavirus and you spray your spray bottle, basically what happens is you have a 4-stroke cycle, a very basic. We're not going to talk 2-stroke. You have your 4 strokes. You have basically power, suck, squeeze, bang, boom. All right. So it goes up. You have compression. And then at the top of compression, it goes back down, because as soon as you come all the way up to compression, your fuel gets injected. So all of the heat of the compression, because remember we talked about compressors, they produce a lot of heat as they're going through because of the energy they're producing. They come up all the way up to their topmost level. Fuel gets injected into it, and then it basically explodes. But there's no ignition source. There's nothing of a spark plug that is actually igniting it. The ignition comes from the heat of compression and also your compression forces. All right, then you have power. Then it comes back up and it goes to exhaust. Then it goes back down and you have suction. And suction is like fresh air. All right. So this wouldn't happen necessarily. Yes, you would need, with a diesel engine, all of your computer and everything like that would be running. It would be running poorly. But if you had a very mechanical system, all right, we won't talk about all the mechanic systems of it, but if you were getting into a mechanical system, it would still be able to run. You wouldn't really necessarily need a battery or anything like that. So,
all right.
That is one way, just for your own knowledge of how to diagnose an alternator. If your car dies randomly, then it's a bad alternator when you're driving. If you need to jump, and then once you're jumped, you're good to go and you can continue to drive, that's a bad battery. All right? And that's just a quick way, but there is other ways to tell. And if those ways are also determined by using a voltmeter. All right? So part of a third engineer's job when you go out to sea is doing, well, everyone has something called Sunday rounds. All right? Sunday rounds are usually the nice, easy day. It depends on the vessel, but sometimes even the deck department will get Sundays off. So all the ABs won't actually be working on Sundays. Some ships, it's more of a relaxing day. It all really depends on where you go. But Sundays at seas is usually, you do your Sunday list. No hard work, no projects that are going to be done, get done on the vessel. So one of the main things that a third would do is battery checks. All right. And battery checks are, you go around to all of your generators, including the emergency generator. You probably have 2 generators on board the vessel. If it's a straight shaft, if it's a diesel electric, you might have 4 generators. But what you do is you go up to the battery. All right. And you have these little terminals. All right. And sometimes you'll have 2 or 4. It all depends. But what you do is they, just like here, you have an alternator. The alternator is basically your generator. All right, because on a generator, all you really have is an engine and it's supplying an electric generator, which is your alternator. All right, and these batteries, since it's a diesel engine, aren't regulating spark plugs and headlamps and radios and all this other stuff. Well, it's probably regulating radios for the deck department, but what it is doing, it's your backup power to restart your generator, just to give you enough power to start up. All right. It will be an air start, but this is to give you all of your electric controls. All right. So what you have to do is you go through and you do your battery checks. And what you're going to be basically do is use a little switch. All right. And let me see if I can actually find a quick picture of one. Battery charger. Come on. Now, these aren't wheeled around either. They're not like something that you would have to switch over or anything like that. Some ships will have, you switch from 1 week to the next week. You go battery bank 1, battery bank 2. Here we go. Here we go. Are you guys seeing the
Yeah.
All right, so this is basically a battery charger right here. All right, it's a 3-phase. Now, usually what they'll have that comes off of it is basically like a little black switch. All right, and it's just a little switch that goes. It's a little switch that just goes up and down, and all you're doing is just turning your battery charger off. All right, but this is what a battery charger looks like. All right, battery switches. So sometimes you can have them that look like this one right here. You guys can see my mouse, right? Okay, good. So this one's just an on and off. Sometimes
That's what we got. You got the Perco one.
You got that purple one right here?
No, the Perco, the red one with the black switch.
Red one.
First one.
Yep.
Yeah, we have that on both our boats.
So that one's just basically, so you would have one going to each battery, right?
Yeah.
Okay. So sometimes you'll have that version. Sometimes it will be a version of, let's see if we can find it. You'll have like, here you go, 1, 2, or all. So right here. All right. And these, the way they operate is you have battery bank 1, you have battery bank 2, and then you want to charge both 1 and 2 at the same time. And then you have your off position. All right. Sometimes you guys will see that. Most likely it will be a variant of this. You might have this one here. I've seen that a bunch. I can't seem to find the the version that I want to show, which is just a little black switch. They look like something you shouldn't touch, but it's basically just a battery charger. Unfortunately, it might not just be on these consumer grade ones. So let's go back into the PowerPoint. So you basically have a little switch there that you have to operate. And what you do is that you turn the switch off and you let it sit for a few minutes. All right. And what you're trying to do is you're trying to get any of the charge that was, as you charge up a battery, all right, it's going to not like necessarily like overcharge it, but you will get to a point where if you take your battery charger and you go to the off position, we're in off and we click it off right away, and you take a voltmeter and you put it on the 2 terminals right there on that battery, and these are 12-volt batteries, what's going to happen? What will it read?
12.4, 12.7, something like that.
So that's what you want it to read, all right? And when you're going to be checking these batteries, what you're going to do pretty much every Sunday is you take your volt reader, and if you go to off and you quickly look at these batteries because you want your job to be done, and you know the chef's making some good pancakes that you want to eat that morning, you'll run into a spot where you'll actually read about like 16 volts. All right. And that's not like it's overcharging. It's the aspect is that it basically still has like a little bit, it's just overcharged. So you have to let it sit for a few minutes, like 5-10 minutes without being charged.
Is that bad? If it's up there, because I know it's supposed to be between 12 and 13. If it gets up to like 16 or 17, is that bad?
It's not great. You should probably start looking at it as far as like your charger. Maybe the charger might be set to the wrong type of battery. It really all depends. Oh, there we go. So, but it could be up there. All right. Now, it's not going to read like 24 volts. That, you know, you have a battery explosion there. But the aspect is that you want to basically give it a few minutes. All right. You want to almost like burn the extra charge off of it. Let it kind of sit and settle and find its good spot. All right. So you go up to it, you get a reading. All right. So you turn off your battery charger because you don't want to be reading what's coming out of your alternator. You want to know if these batteries are bad. All right. So you read your voltmeter, you get it. Basically, you take your positive terminal, you take your red terminal, and you go to the positive, you take your black terminal, and you stick them on the 2 probes, and you get a reading. What happens if you do it in reverse? What if you take your black and you go to your positive terminal, and your red and you go to your negative terminal? Does the world blow up?
Wouldn't be good.
Wouldn't be good. What happens to the voltmeter that you have?
It just reads it as a negative voltage.
Exactly. So there's absolutely no difference between taking a voltmeter and reading it in reverse. All right. All you would get is just the negative voltage reading. So instead of getting something like 12.04, like a positive 12.04, if you take the black lead and you put it on the positive side, you would just get a negative 0.04. That's all what would happen if you just put the 2 probes in reverse. All right. It's just which way we're taking our readings. So you just take your readings, and usually these things will have like this would be like generator 1, and you would have the forward part of your ship, and this would be your aft. And basically you would have generator 1, aft voltage is like 12.04 today, and this one is 12.16. So you would just take it and you note it, and you look for trends every week. You're trying to look for if these batteries are going bad, because these batteries are your lifeblood. Captain that I sailed with was on a vessel one time that went out. They had an issue with their vessel and they lost all power. They blacked out the plant. It was a diesel electric. So they basically, once you black out your generators, you have to bring them back online. Well, they couldn't. All of their batteries were dead on board the vessel. Every single battery. Which sounds crazy to hear, but everybody who was checking these batteries basically checked them with the battery terminal switched on. So they weren't actually getting a reading. All they were reading was, hey, the alternator is putting out proper voltage. That's great. You could tell that by the lights being on. So when the time came to actually use these, they were unable to, and they were adrift at sea for like 3 days before they can get an offshore tug to go get them. And while the offshore tug was on their way out there, the company hired a fishing vessel, like a local fishing vessel, to drive out batteries to them. That was a very expensive day for that company and for that whole entire boat.
Fishing vessel did good.
Yeah, they did very good. They didn't have to work and catch for a little while because they had to go all the way out to sea. They were in the middle of the Gulf. So that's like a Sunday at sea that you would take care of. That would be part of like what a third would do. All right. Another thing is to feed the MSD system, like we talked about about a month ago. But these are just some easy jobs. You just walk around. You're taking voltages off your batteries. It's really not too bad. But make sure when you're doing it, you turn off your battery charger. So let's erase this nonsense. So before we get into all of that, because I think that's slide 15. Yeah, let's do that, and then we'll be done. I thought this was going to go into deeper. So the TSES. That's what I want. There we go. So right now, on the TSES, this is what you would have. If everything's okay and you still have power, you have ship's power coming through, and I have black marker, which isn't good. So ship's power comes through, you're charging your batteries, and when you want the general alarm to signal, right here, we have a new symbol. These are switches. All right, so each one of these represents a switch. All right, they can also be drawn like that. That's a single gang switch, so it's basically one switch makes contact in one direction. It'll either go, it's either open or closed. And then you can have switches out there that look like this. All right, where it has a position where it can be closed in this direction or closed in this direction. All right. So one of the three locations that you could have for the general alarm, someone signals one of them, it closes the switch, and now it's powering our general alarm. And that's a term that I just used. I said closed. All right. So if you were to close a switch or close a breaker, what is happening and why is that different from when we talk about valves? What are we physically doing?
You close the switch or breaker, it's activating it, but when you close a valve, it's deactivating it.
Exactly. So when you have a valve and you close the valve, right, you're stopping the flow. But when you close a switch or you close a breaker, That's allowing flow to go through. That's allowing your current to go through. All right? That's a terminology you have to get straight in your head and keep straight. If someone's going to open a breaker, it means when you open it, you're now not allowing flow to go through. That is when you're going to be in a safe position. Or when you close a breaker, you're activating the circuit. All right? You're energizing your general alarm. You close your breaker, you're going to start your pump. All right? Make sure you guys keep that terminology straight in your head. So when we close or we push this button, and pushing the button will close this switch and start our general alarm. All right? We open this switch, the alarm is deactivated, and we're charging our batteries. All right? If we lose ship's power, we now have these 4 batteries, 1, 2, 3, 4, right here, as our backup for our general alarm right now. So if someone closes that switch, that power is still going to be able to sound our general alarm without ship's power. All right? That's another reason to have these batteries. And there's batteries all aboard the vessel. All right? They're not just attached to the generators. They're not just attached to our emergency generator. They're up on the bridge. There really could be any number of what vessels need them for. All right. They're above the bridge. They're on the flying bridge. So there are 2 24-volt DC systems on the TSES. So you have your ship's power coming in, and these are 2 different battery chargers. All right, and they're both putting out DC power right now. That's coming from our AC generators. All right, one of them goes to our general alarm circuit and basically our battery bank. All right, the other goes to our internal communications, our navigation, our instruments, etc. Anything that has to do with what the bridge needs to operate in a time of crisis, basically. All right, and again, it's going to be charging our battery backup. So normal flow is going to be doing both. They're going to be charging the batteries, and they flow out to our general alarms. All right, but this is a parallel circuit. All right, so if you lock off here, you would still have flow going to your batteries. All right, and returning. Same thing here. If you knock out right here, you will still have normal flow going to your internal communication circuit. Granted, you don't want to cut this line right here because then you don't have your general alarm circuit. But that being said, this is a parallel circuit. They are running in parallel. They are running in series, and you lop the section where you had a battery, and then it goes to your general alarm circuit, and you lopped anywhere on here, you would unable to charge the battery, and you wouldn't be able to run this circuit. And that is a series circuit. Right now, these are running in parallel. Why is it so? What is the biggest factor in life that you would have a parallel circuit? Why is everybody always going out and buying new Christmas lights instead of using old ones?
Because they're in series, so if one light breaks, they all break.
Alex had it right. What's it?
Because the battery dies easily.
Say again?
The battery dies easily, like over time.
If you have a series Christmas light or
like any kind of light in general.
So yeah, We're not going to talk
Because if
about
you leave
batteries,
it-
but what if you have a parallel circuit?
Oh, doesn't the circuit like break down or something?
Doesn't
Over time.
necessarily break down. So what happens
A
if you
single
have?
bulb.
So if you miss a bulb in a parallel circuit, what happens to the rest of the circuit?
Nothing.
It flows because it's parallel. Because you have
Oh yeah,
you
flow
have
continues.
extra circuits. You have extra. If you have a parallel circuit, then if you miss one bulb, the other circuit can activate the other bulb. So just keep flowing.
All right, so let's bring this to the big screen. You guys got the whiteboard?
Yeah.
Okay, good. So if you have a power source, all right, and this is going to be a parallel. And we have this does not give me a good drawing. So we have light 1, light 2, light 3, and light 4. All right. I'm not going to use this whiteboard application again. So that's our power source. If we lose light bulb 1, what happens to 2, 3, and 4?
They all go
They don't
out.
light.
There's no flow.
There's no flow of electricity,
Yeah.
right? They'll burn out. But what if you come up to them? You turn on the switch, all right? You have your switch right there, and you turn it on, and you leave the room. Oh boy, that's a big one. You leave the room. All right, so you turn on your switch. And then you come back in a few minutes and none of the lights are on, but you have your switch is in the on position. How do you know which bulb is out?
Oh, the first one.
You don't know which bulb.
You don't have a freaking clue.
You don't have a clue.
But in parallel, you have different pathways for it, so you can easily figure out which one is out instead of trying to just take them all out, and then you don't know which one you would have to fix.
So if we have a parallel circuit,
Wait, I'm not going to. The top one is in series, right?
yeah, the top one's in series.
Okay, yeah, okay.
One, two, three, 4. All right, same thing. 4 light bulbs. We go to the on position in parallel. And we come back, and one of the light bulbs are out. How do we tell which one is out?
The only one out.
You'll know which one's out,
Yeah.
right? Because it will be out. So in a parallel circuit, we still have the ability to have flow going through each one of these. And if 3 is out, we'll still have the ability to have flow going through 4, 2, and 1. All right. But in a series, you will have no idea which one's out. If you weren't there to see these bulbs go out, if light 1 is out, it blocks 2, 3, and 4 from completing the circuit. You will have no flow. All right. But if light 1 is working, great. Flow's going through it. Light 2 works. Good. We continue through. But if light 3 is out, it stops our ability to have flow. So we will have no flow that goes to 4. 4 won't be on, but also 2 and 1 won't be on, and neither will be 3, because we don't have the ability to complete a whole circuit all the way through. Like in parallel, we have the ability to constantly have flow going through any of these. All right.
Oh,
And this
so
is
Christmas lights are like series, right?
say again.
So Christmas lights are like the series.
So yeah,
Like
older Christmas lights that you see, and people sitting there and having to check a bulb through an entire string of lights would be like a series string of lights. They're cheaper to make because you only have to use a piece of copper wire to connect from line to line. All right. But if you're using a parallel, you have to have every single bulb have their own circuit to go back to the power source. Which is why you would see with certain Christmas lights that you would have like maybe a section of like 5 or 10 bulbs. They'll be in series together. And then there's a jumper that goes through. And they'll make a section of 5 bulbs. And then they'll have another section of 5 bulbs. So those 5 bulbs will be in series. But that 5 bulbs will be in parallel to another 5 bulbs. All right. So that would look like something like this. And we're only going to do 3 because that still gets the point across. All right, so you still have your power source here. But these 3 bulbs, 1, 2, and 3, are in series. 1, 2, and 3 are in series together, but they're in parallel to 4, 5, and 6. Just like 1, 2, and 3 are in series, but they're in parallel to 7, 8, and 9. 7, 8, and 9 are still in their own series. All right, so if bulb number 5 bust, what happens to 1, 2, and 3, 7, 8, 9, 4, 5, 6?
Oh, they don't get the energy.
Do all of them not get their energy?
Actually, no. Oh wait, this is a parallel, right?
It's parallel and
Partial parallel.
So you have.
So there's still flow going on, but from 1, 2, and 3, and 7, 8, and 9, it's just 4, 5, and 6 doesn't get the power, right?
Yes. So 1, 2, and 3 will be lit. 7, 8, and 9 will be lit, but 4, 5, and 6 will be dark. All right.
Wait, if 5's out, how come 4 can't get power?
This is a partial parallel.
So if we follow the line, 4 is only going to have a supply of power. They don't have their return. It's broken right here at 5. 5 won't be lit, so it's a series of 4, 5, and 6. But 4, 5, and 6 as a combined unit, as one singular series unit, is in parallel to the unit of 7, 8, and 9. Okay? So 1, 2, and 3 are unbroken. They can have their power returned and have a constant replenish of power, of electrons going around. Same thing with 7, 8, and 9. Their power is still going all the way through, and they're going to be able to be replenished. But 4, 5, and 6 are broken at 5. All right, so that would be a situation where, like we said, we have a partial parallel. All right, but this is what it looks like as far as newer Christmas lights. You remove one light bulb and a section will go out, but not all of them. Because a section of them are in series, but each section is in parallel to another section. Does that make sense? Is anybody still confused on this? Okay, good. So, class is pretty much over as what I wanted to get through. I actually got through a lot more of what I thought we were going to today. I I will see you guys on Wednesday. So remember, quiz Wednesday from basically slide 1 to slide. Let's just go to slide 15. All right, slide 1 to 15.
Professor.
What's up?
So it's going to be in a different format, right? The quiz.
Yes.
All right.
So it's just going to be in. What do you call it? So you're basically, it's going to look like a normal test. All right. So it's going to be, question 1, question 2, question 3, all on the same page. Okay.
All right. Have a good day, Professor.
Have a good one.
Have a good one.
Take care, Professor.
Good rest of your day.
Have a splendid Monday afternoon.
Have a good day.
Have a good one.
Oh, my computer kind of disconnected like like a good amount of the way through it. Did you see that? And then I came back in.
Yeah, I saw everyone. If just keep coming back in if you disconnect. All right. So I get a notification that pings me if you try and come back in. So I try and get to you quick.
Okay, thanks.
All right. Oh, you muted yourself.
Okay. Have a nice day.
Have a good one. Everybody else good?